Let's now a bit more formally define what a transaction is and what a schedule and a history is. So a transaction, as we have seen already in the previous examples, is like just a sequence of read-write operations and also can have an abort or commit. These individual data objects here we call X. This example are just like, let's say, variables like data records or parts of the record we are modifying. Doesn't really matter for our considerations here. We say that a transaction T is a partial order between these steps. That means that not all of these pairs of actions, read-write, within one transaction have to be ordered. Only read-write operations to the same object or multiple writes have to be ordered. This is more like a theoretic observation or consideration. In the end, when we are writing transaction in an inline way, we're writing read-write and so on, then the order here is of course given from left to right, but in general you don't have to order or assume any ordering between, let's say, two reads to different data objects from the same transaction. A complete transaction has as a last step either an abort or a commit, also not surprising. We can specify for these partial orders a complete order when we are really writing down from left to right. That means we are specifying also for the non-ordered elements some arbitrary order. And as I said, if you're writing them in this inline fashion from left to right, then anyway we would assume the order to be given as we have written it down. Since we're talking about concurrency control, of course we're not looking at individual transactions separately, but we're looking at them as a set of transactions, and we have to decide later on if this is serializable, right? It's like the task we have. So now look at this set of transactions T1 to Tn. Each transaction, as defined earlier, consists of a set of operations and an order between these operations. And now in a bit sloppy notation, a history for the set of transactions contains, first of all, the operations from the individual transactions and defines also an order over this, you can say, union of the individual operations from the transactions. So this is like the mathematical definition you can go through to match with the next slide, which is a bit easier to understand in the beginning. And before we go into that, we also want to say what a schedule is, because a history always considers that these individual transactions are committing within that history. And we also say a schedule is a prefix of a history. So without looking at the mathematical details from the previous slide, we can explain what they mean, these points A to E, which is kind of easy to understand. First of all, the point A says, the history contains all operations of all transactions. And this makes a lot of sense because we're looking at transactions, and transactions have operations. And if you're looking at a history, which is like these transactions completely executed, then of course this history should also be complete in a sense that it does not avoid or does not drop any action by the individual transactions. A history, other than a schedule, requires one terminating operation for each transaction, one and only one. The history adheres to the operation order given within the transaction. That means transaction defines an order, and the history has to adhere to that. However, for the operations which are not ordered, the history does not have to come up with an ordering, so it's also partial in that sense. And then point D is that the terminating operation is of course always the last operation in each transaction. So after the commit or the abort, there's no other action coming for one transaction. And conflict operations are ordered. So the history is defining for the conflict operations. So access is where one at least is a write to the same data object, an order. Because of the first two properties, A and B, a history is also called a complete schedule. A prefix of the history can also be history itself. And since histories are considered special cases of schedules, usually it is sufficient to talk about schedules. And here comes now a very central definition, since we're talking about serializability. What is a serial history? A history as a serial, if inside this history, if you're looking at pairs of transactions, Ti and Tj, where I is not equal to j, either all of the operations from Ti occur before all the operations from Tj, or the other way around. So it means if you have a schedule or history S, then we say it's serial. For instance, if first of all there are all the operations coming which stem from T1, T2, then all from T1 and all from T3 and all from T4. Then this is a serial history or serial schedule. It would also be fine if there's T1 and then T3 and then T1, T2 and then T4, but there should not be any mixture between the individual operations. So as an example, consider transaction T1, T2, T3. Each of them is depicted here in this illustration on the bottom as a directed acyclic graph. It is a partial order, because here we only say, for instance, that R1 is reading X before writing X, and reading Z before writing X, but we do not specify any order between these two here. Now, if we want to define history over these, we have to come up with an order of conflict operations. And for instance, here we have a write to X and a read of X. So this is certainly a conflict operation. So we come up with a partial order between these individual transactions, as we can see here, by introducing these dashed blue arrows. So this is now our history. History because also we see that all of these transactions are committing in this case. Now if you want to define a possible total order via topological sort, we can write it down like this. It's one way. Important here is that this total order is of course adhering to the partial order. That means all of the arrows here are reflected also in this left to right written total order. If you're looking at histories or schedules, we can define the following sets of transactions derived from individual schedule. We call trends of S simply all of the transactions which are included in the schedule. We write commit S for all the transactions which are committing. That means CI is part of the schedule. Likewise, the same for abort. And then we can define active S to be the set of transactions inside this S schedule, which is all the transactions minus the ones which are committed or aborted, so the currently active ones. Of course, we have transactions of S, the trends of S is a commit S union abort S in the case of histories, because in history we said that each of these transactions has to either commit or abort. And this also means that we don't have any active transactions inside a history. For a schedule like this, S1, it's easy to see that we have the following sets of transactions: committed transactions, aborted transactions, or active transactions. So we see here we have two committed ones, which are making this set, and one aborted one, which is this set, and there's no other transaction, so the active ones are empty. And similarly here for the schedule S2 as an example. The goal for the next minutes will be to come up with the formal concept of serializability and to understand or to derive different classes of schedules and to see if these classes of schedules are prohibiting these anomalies we have seen earlier. In the end, we will have something like this. We will see here this is conflict serializability class and refinements of this, and also more general classes that we call final state serializability and view serializability.